what kind of symmetry could this have? So it has two things, and it's in 3 dimensions, it's 3 equations. So you can ask yourself, what kind of symmetry you can have in M equals R3, Euclidean world of 3 dimensions, like this room, such that the symmetry group has 2 elements. Group has this structure, and by closure, repeat of the elements should be the same. And I'll just give you the list of what one can have. One can have reflection. One can have rotation. And one can have inversion. So I'll write them explicitly. So there's only one non-trivial operations. So inversion is the so-called parity operation. So if you have a point at x, y, and z, parity operation means you just get it inverted through the center. Reflection, I'll use word sigma for S for word for reflection in any language other than English, like specular or like spiral or spiegel, mirror, etc. So you take x, y, z, and you just invert one of the coordinates. So what happens in this case, if I'm in the origin and I have a point, then the other point will be, this is my point, the inverted point will be here. Just inverted through the origin. This guy will have a property that this is x, y, z. If I have a point here, then it will be inverted there. So if this is my x, this is sigma x. And you actually also have a rotation. So I'll use notation C having to do with cyclic, 1/2 having to do with cyclic rotation by half of a whole circle, or half of 2 pi. So you take x, y, z equals, and rotation, what it'll do is I'll rotate around z-axis. So here's my z-axis. So if I have a point here, someplace here, by rotation by pi, the rotated point will end up here. So this is x, this is x. So that means both x and y will change sign, but z will not. Z is a space. This whole line doesn't get changed by rotation. That's so-called invariant subspace. And that's a complete list of discrete operations you can do in 2 dimensions, 3 dimensions. And they're qualitatively different. You change either 1 sign, 2 signs, or 3 signs.